So in this short video we're going to discuss the Gibbs free energy as a function of temperature for solids, liquids and gases. So solids, liquids and gases are all phases of matter, and in this course we define a phase as a homogeneous portion of matter with uniform properties and composition. And in particular for solids, liquids and gases, that's what we're focusing on. So this is the picture that you're all aware of for these different phases. So a gas has these component particles far apart from one another. In a liquid and a solid they're condensed. In a liquid they can kind of move over each other. In a solid they're fixed. And you're all aware of this picture. There are other phases that exist: colloids, liquid crystals, plasmas, gel solutions. They're not on this course, but we might talk about them a little bit, and they're going to be on other courses that you do during your degree. So what is the equilibrium phase? Well, what do I mean by that? So for a given set of thermodynamic conditions, like the temperature and the pressure, which phase is the one that exists? So we know that at ambient pressure, that 100 degrees centigrade, liquid water turns into steam, and we also know that at 0 degrees centigrade liquid water turns into ice. So why does this happen? Well, the equilibrium phase, which is the one that exists for those thermodynamic conditions, is the phase with the lowest Gibbs free energy. The Gibbs free energy was something that you were introduced to in the first half of this course, and it can be written down as a balance or a sum of these terms. So this is the internal energy U, this is an energy term, so these are all energy terms. That is related to a kind of volume that the material takes up, and this is a energy term related to the entropy, and it's a function of temperature. So S is the entropy. Sometimes it's written like this. This H is again something you were introduced to. It's called the enthalpy, and it simply just sums up the U and the PV terms. And note the balance. So at some temperatures this negative term will be large as a function of temperature. At very high volumes this term will be large. So these are the things to think about, and we want to work out for different thermodynamic conditions which is the phase of these with the lowest Gibbs free energy. So let's think about this for solids, liquids and gases. Right. So for a solid, and we're going to come on to more explanations of why this is so, the U, which is the internal energy, is large and negative. So these atoms form positions where they're attracted to one another, as we found out, but they're not too close to have overlapping orbitals, and so they minimize their energy, and their internal energy is large and negative. So the S is low because they're ordered, which means that this term here is going to be low. For solids there will be a temperature dependence, but it will be low in general, and the V is very small, so this term will be close to a minimum value as well. So for a gas, of course, the atoms are far apart. They're still attracting one another, but they're not as close as they'd like to be, so the U is negative but very small. Right. The S is very high because the gas atoms are disordered, so when there's a temperature dependence there's more of a temperature dependence for gases than there is for solids, because S is intrinsically high for a gas, and the volume of course is very high, so this term is large as well. For a liquid we have a similar value of U to a solid. The atoms or the particles are close together. The S is slightly higher than a solid, because this is slightly more disordered liquids, as you know, than solids, and the volume is similar to a solid too. So let's think about how when we look at G as a function of temperature, this was our aim in the first instance, so we can do G as a function of pressure and G as a function of volume, but for the first instance we're going to think of temperature, which phases are going to be in equilibrium. So here's G as a function of T for solids, liquids and gases. And I plotted it on these axes here. So let's first plot it for a solid. So we know that it's quite low to start off with because this term is negative and large. And as we increase in temperature, then of course this term starts to get bigger and bigger. So this gets more and G gets lower and lower, but at a relatively modest rate. For a liquid, we have a slightly less starting point at low temperatures when this is very small, so this term dominates. And at higher temperatures, we again decrease because this term's getting larger and larger, and S is intrinsically higher for a liquid than a solid, so it's larger here. And then for a gas, we have this situation. So at low temperatures, U is much less negative, but as we increase in temperature, this term gets drastically bigger, seeing as S is so large. And then we can look at here, which of these phases is going to exist at a particular temperature. We just look at which of them has the lowest G. So here, up to this temperature here, the one with the lowest G is the solid. Then at this point here, which is the melting temperature, the liquid has the lowest G, so this orange curve has the lowest G. And finally, at this point here, the gas has the lowest G. So the gas is the equilibrium phase. So at high temperatures, the gas is the equilibrium phase. At intermediate temperatures, the liquid is the equilibrium phase, and at low temperatures, it's a solid. So we should remember that when we did this calculation of G as a function of temperature, we kept P and V fixed. Now, of course, G will also depend on P and V, and in general on these three different terms, P, V, and T, the thermodynamic variables. And depending on your pressure and your temperature and your volume, you'll have a different equilibrium phase. We're going to talk about that later on in the course, but quickly, so you can answer the PST question on this, let's define what we mean by a phase diagram, and I'll show you a picture of one. So a phase diagram is a map of the equilibrium phases plotted for two or more variables. So let's have a look at the carbon dioxide phase diagram. So on this axis we have pressure, on this axis we have temperature, and it's a map of which phase is the equilibrium phase for a given pressure and temperature. Now we're going to talk about these phase diagrams more, and I'm going to show you some examples and do some experiments. You can look forward to that. But for the problem sheet, what you can see is that when we fix a pressure and we look at the equilibrium phase as a function of temperature, we were drawing a line up here somewhere. So at low temperatures we had the solid, higher temperatures we had the liquid, highest temperatures we had a gas. Now, as you probably know, at ambient pressure, so this is at 1 atmosphere, if you draw the line here, the liquid phase, if you think about this, so it's fixed pressure and we're looking at the Gibbs free energy as a function of temperature, the liquid phase never wins. We go straight from a solid to the gas, and it sublimes. And then the final thing is this point here, and we're going to talk about this in more detail, but this is called the triple point. And at the triple point, we have one point here where actually the solid, liquid, and gas phases are in equilibrium. So they all have the same Gibbs free energy, and we're going to talk about what it means for phases to be in equilibrium. Like on this line here, the gas and the liquid is in equilibrium. On this line here, the solid and the liquid are in equilibrium. We're going to talk about that more later in the course.